Welcome to this explainer. Today we're embarking on one of the absolute most fascinating journeys in human history. We're looking at our centuries-long quest to externalize reason, to literally take the burden of complex thought and calculation out of our own biological brains and delegate it to machines. It's this incredible story of vision, where the most brilliant minds across history tried to build physical artifacts that could actually process logic.
Okay, let's dive into this. How exactly did we teach raw materials, like brass metal and refined sand, to think? This entire journey is driven by a series of escalating human problems. You see, every single time our ambitions outgrew our natural capacity to crunch numbers, we had to make a profound conceptual leap. We didn't just build faster tools, we fundamentally changed our entire understanding of what it actually means to process information.
To understand the devices we use every single day, we're going to walk through 4 key eras. First, the dawn of mechanical minds. Second, abstract logic and universal machines. Third, the silicon miniaturization miracle. And finally, the personal computing revolution.
All right, let's start with Section 1, the dawn of mechanical minds.
So, we have to rewind a bit to early modern Europe. Navigating oceans, engineering massive structures, all of this required highly precise math. But computers back then, well, they were actually humans, and human computers were notoriously slow and prone to making mistakes. This really frustrating bottleneck sparked a massive philosophical ambition. The 17th century mathematician Gottfried Wilhelm Leibniz captured it perfectly with his famous command, "Let us calculate." He envisioned this world where disputes could be settled just by turning the crank of a machine, effectively making thought deterministic. And people actually started building these wild dreams. Back in the 1640s, Blaise Pascal built a small box called the Pascaline. It used interlocking geared wheels just to help his tax collector father add and subtract automatically. When one wheel did a full rotation, it physically carried a digit to the next. Pretty clever, right? By 1673, Leibniz himself built the stepped reckoner, using a drum mechanism to multiply and divide. But the biggest leap? That came in the 19th century with Charles Babbage's massive, room-sized steampunk vision. He designed the difference engine for polynomial functions, and then, astoundingly, the analytical engine. Babbage designed a machine with a mill for processing and a store for memory, using punch cards for instructions.
The contrast here is just stark. We move from human computers, exhausted and inevitably flawed by human fatigue, to deterministic brass gears. They represented abstract numerical operations embodied in actual physical components. If the gears interlocked correctly, the machine simply could not make a mathematical error. It was the birth of automatic precision.
But, the most beautiful conceptual leap of this whole era didn't actually come from Babbage. It came from his collaborator, Ada Lovelace. She looked at his analytical engine and realized something completely earth-shattering. She saw that the machine wasn't just crunching numbers, it was manipulating symbols. And if a number could represent a musical note or a letter, then hey, this machine could compose music or create art. She completely reframed computation from mere math to universal symbolic manipulation, which rightfully earned her the title as the very first computer programmer.
Moving on to Section 2, abstract logic and universal machines.
As we hit the 20th century, the problem of calculation shifted from physical brass wheels to pure theoretical logic. The mathematician David Hilbert had posed what he called the Entscheidungsproblem, basically asking if there was a systematic method to determine the truth of literally any mathematical statement. Well, in 1936, a brilliant mathematician named Alan Turing responded. He didn't build a physical machine, he built a mental, mathematical model, the Turing machine. It reduced all calculation down to simple symbolic operations on an infinite tape.
Now, what's really interesting here is how beautifully simple Turing's concept is. The machine basically does 3 things. It reads a symbol on a tape, processes it based on explicit rules, and then writes a new symbol or moves the tape. That's literally it. But Turing mathematically proved that a single universal Turing machine could simulate any other machine just by reading its description encoded on the tape. This was a total game changer. It was the birth of the stored program concept. He completely separated the physical machine, the hardware, from the instructions it was running, the software.
Of course, Turing's highly abstract math didn't stay theoretical for very long. During the Second World War, practical necessity came knocking. At Bletchley Park, Turing applied these exact abstract insights to cryptanalysis. He designed the Bombay machine, automating the logic required to decipher German Enigma communications. This absolutely proves how deeply powerful these concepts were.
This mechanized logic was successfully weaponized to shorten the war and save countless lives. In the post-war era, Turing's theories basically became the invisible scaffolding of our modern world. The von Neumann architecture physically realized Turing's stored programmed concept, placing both instructions and data into the exact same memory bank. By 1950, Turing was already looking ahead, proposing the Turing test to reframe machine intelligence as conversational indistinguishability. The logical foundation was now perfectly laid out for us.
Which brings us to Section 3, the silicon miniaturization miracle.
So we had the logic, right? But actually executing it was physically unsustainable. Early electronic computers like the ENIAC relied on these fragile glass vacuum tubes. The ENIAC was literally the size of a large room, generated blistering heat, and supposedly even dimmed the streetlights of Philadelphia when they turned it on. We desperately needed to move from fragile, hot glass to solid, stable stone, specifically the tiny, modular, cool, and highly reliable silicon transistor.
I want to emphasize this. The trajectory of human history changed forever in one specific year, 1947. At Bell Laboratories, John Bardeen, Walter Brattain, and William Shockley invented the transistor. By using semiconducting materials like silicon, they found a way to amplify and switch electrical signals without the immense heat and unreliability of vacuum tubes. It was, without a doubt, the absolute breakthrough of the century.
Because transistors were solid state, they introduced something crucial: modularity. Engineers started combining them into logic gates, and then the race to shrink them was officially on. By 1971, Federico Faggin and Ted Hoff introduced the Intel 4004, which was the first commercially successful microprocessor. They somehow figured out how to integrate thousands of microscopic transistors onto a single silicon die. Computing power that used to occupy an entire air-conditioned room could now easily sit right in the palm of your hand. And this brilliantly illustrates what happened next. It followed an exponential curve known as Moore's law. Gordon Moore observed that the number of transistors we could fit on a chip roughly doubled every 2 years. But remember, this wasn't just some economic or technical rule. It's a profound philosophical principle. It shows humanity recursively accelerating its own tools. We were literally using better computers to design even smaller, faster computers.
All right, final part, Section 4, the personal computing revolution.
So the hardware problem? Solved. But now we had to figure out how to democratize it. Computing couldn't just belong to the military and massive universities anymore. In the 1970s, it finally burst out of the lab and into the garage. The Altair 8800 completely captured the imagination of hobbyists, proving you could actually own a programmable system affordably. Then, visionaries like Steve Wozniak and Steve Jobs took it a massive step further. With the Apple I and II, they combined technical ingenuity with user-friendly design. They made computers robust and approachable, bringing them straight onto people's desks. But to truly get this into the hands of the masses, people needed to do more than just wire hardware together. This is where software took center stage. Figures like Bill Gates and Paul Allen recognized that operating systems were the absolute key to mass adoption. By creating software that abstracted away all those hardware complexities, they allowed totally diverse machines to run a massive variety of useful applications. Software became the accessible bridge between human intent and silicon logic. What emerged from all this is modern PC architecture, and honestly, it's pretty amazing how history echoes. We have the central processing unit, which is exactly Babbage's mill. We have volatile RAM and non-volatile storage, which is Babbage's store. Add in an operating system and input devices like the keyboard and mouse for direct interaction. This architecture fundamentally redefined what it actually meant to use a computer, turning us from passive operators into active participants. And this is exactly why this whole 400-year journey matters to you today. By operationalizing Turing's theories onto microscopic silicon chips, computing ceased to be this remote, industrial force. It became an intimate, everyday extension of human intellect. From learning and experimentation to global e-commerce and digital culture, these localized devices rapidly linked up, creating the seamless, always connected internet age we inhabit right now. We've gone from turning brass gears by hand to literally holding supercomputers in our pockets that connect us to the entire globe. So I want to leave you with this provocative thought to reflect on today. We have successfully externalized our logical reasoning into an always connected digital ecosystem. As machines now begin to learn, generate, and seemingly understand, what is the next frontier for human intellect? Thank you so much for joining me on this explainer. Keep exploring, and I'll catch you next time.